Hello everyone. In this video, I am going to talk about Chapter A, Friction, which includes Section 8.1, Characteristics of Dry Friction, and also 8.2, Problems involving dry frictions. Friction definition is defined as force of resistance acting on a body which prevents or resists the slipping of a body relative to second body. So experiments show that frictional forces always act tangent or parallel to the contact surface in a direction opposite the relative motion or tendency for motion. So, in other words, the direction of the friction will always be parallel to the contact surface. Also, it will be the opposite direction of the direction we're trying to move or actually moving. For the body shown in the figure to the in equilibrium, the following equation must be true. Well, first thing you have friction force equals the P, which the P is the force pulling to the right. And then vertically, you have normal force equals the weight. And also, we're going to write an equation about the moment. W times X equals P times H. Summation of moment about this contact point, this point O right here. Uh, Next thing, to study the characteristic of a friction force, F, we're going to assume that the tipping does not occur. What it means is that we're going to assume H is small and A is very large. We'll gradually increase the magnitude of the force P, and typically the experiments here shows that the friction force F varies with P, as shown in the right figure above. So what I mean by that is that, say for example, I have a box on the table not moving. Okay, I'm gonna draw it 3 times. If it's not moving, let's say I push with 10 newtons of force, not moving, that means the friction is going to be, because they need to be in equilibrium, that means the friction will be 10 newton going on the other way. So if I push this box with a 20 newton of a force, not moving, this thing not moving, that means at the bottom the friction is going to be 20 newton. Okay, pardon the sketch over here. And if I push with 500 newtons of force, if this thing is not moving, then that means the friction at the bottom will be 500. So that's what I mean by friction force varies with P. As long as it's not moving, the more you increase on the force that you push, the more friction that you see. Friction only will change the moment it actually starts moving. So if it's not moving, friction force will be equal to the amount of force that's on the opposite direction. The maximum friction force is attained just before the block begins to move. That's what I mean by, when it's not moving, it's going to increasing, and it will increase to the maximum just right before it's going to move. And what we call that situation, the impending motion. The value of the force is found using F lowercase s stands for static, and then equals mu s and times n, where over here the mu s is called the coefficient of static friction. And the value mu s depends on the contact two surfaces that we contact, how rough the two surfaces are. Now, the mu s here is static friction. That does not mean we always use this mu s times normal force to figure out what's the static friction. Remember what we say, if it's static, it's not moving, your friction force always depends on how much force is being pushed to the object. And the mu s times n here is your maximum friction force, maximum static friction force. So in other words, how much how much that minimum force that we need in order to just start it moving the block right here. And then once it starts moving, we're going to use this equation. Once it starts moving, the friction becomes a sort of a constant. We'll look over here, it's kind of flat and it drops down too, but we're going to assume that flat portion. So mu fk equals mu k times n. So the value mu k here, coefficient of kinetic friction, will be less than your mu s because we've already started moving. Kinetic friction, so it drops a little, just a little easier, a little less than the maximum static friction. So over here, very important to know that the friction force may be less than the maximum friction force. So just because the object is not moving do not assume the friction force is at x and it's at its maximum. So over here, maximum, it's this thing up here, and our static friction increases, that this number changes as it goes. This number changes as we apply more forces to it. Okay, unless you know that this object is impending, then you can use mu s equals fs equals mu s times n, unless it's impending. Only under the conditions it's impending, then the friction equals mu s times n. All right, so by experiment, we can determine the value of mu s. Maximum friction force mu s, fx equals mu s times n, where this mu s is the coefficient of static friction. Then when the block is on the verge of sliding, the normal force N and the friction force Fs combine to create the resultant force Rs. So from the figure over here, we know that tangent psi s equals Fs divided by N, where Fs equals mu s N divided by N equals mu s. Next thing, if we're on the inclined plane and we know how to write those equations, we're going to have a summation of force horizontally, summation of force vertically. And if we put that together, mu s equals w s theta s divided by w cosine theta s. And then together that w, the weight cancels out. That gives us the tangent theta s. Okay, so over here, this experiment, simple experiment, showed us how to calculate the mu s between the two materials in contact. So mu s over here will equal to tangent of theta s. So steps for solving equilibrium problems involving dry friction. First, as usual, we're going to draw the free body diagram, and then make sure in that free body diagram, you want to show the friction force in the correct direction. It will be always the opposite direction of the motion or impending motion. We're going to determine the number of unknowns. Do not assume that F equals mu s n unless it's impending motion, unless the impending motion condition is given. And then we're also going to apply the equations of equilibrium and the appropriate frictional equation to solve the unknowns. So over here, if we try to push this really tall object, that's called a cabinet, we're gonna first need to determine, would it slide or would it tip first? We don't know, so we're gonna make our assumptions over here. So if it's tipped, the point of contact will be on the lower right corner of the cabinet. If it slide, it will be sort of, not, it's not in the middle, but it's not on the very edge. It will be a little to the left of the lower right corner of the cabinet. So over here, you're going to make your assumptions. If the slipping occurs, first one, if the slipping occurs, we know that F equals mu s n, and we're going to solve for x, the p, and n, and then we will check, does the value of x that we get there, is it in between 0 to b over 2? Is it really in between the right half length of the cabinet? Now, second assumption, if the tipping occurs, that means the x is going to go all the way to the right. It's going to be, the contact point is on the lower right bottom of the cabinet. So x equals b over 2. And then in this condition, you will do p, solve for the p, and then f. And then we're also going to check for this f right here. The value of f, after we solve our equations, does the value of f less than equal to mu s times n? Okay, let's take a look at an example. We're going to move this object right here. Okay, we know the weight is 250 pounds, and then we know the mu s equals 0.4. First assumption, we assume it's going to slip. Okay, we assume it's going to slip. That means it's going to be somewhere in the middle of the right half. The x is going to be in the middle of the right half of the bottom. And then also, if it slips, the friction equation says F equals mu s times n. Mu s times n, that gives us 0.4 n. And then we write our sum, sigma fx equal to 0. We write our sum on the vertical direction, sigma fy equal to 0. And then we're going to put these two equations together to solve for the value of x. based on writing a sum of moment about point O. Summation of moment about point O equal to 0, we solve for the value of x. And we calculate that value of x needs to be 1.5 feet, 1.8 feet. And compare that 1.8 and that 1.5 for the actual dimension of the object. 1.8 is greater than 1.5. Okay, look over here, our last one right here. We do need that x to be in between the right half. So, in other words, that value of x needs to be less than half of the width of the object. So ours, compared to that half of the width, 1.5 feet, it's bigger. That means the slipping did not occur. Our assumption that say this thing is going to slip is not right. That means we're going to go with the second assumption, meaning it's going to be tipping over. Okay, so if the tipping occurs, we write our equation horizontally, vertically, and we do an equation for a moment. We calculate the value of p here. Calculating the value of p, we get 83.3. Then we compare with mu s times n. Mu s times n is 100 pounds. That means, hey, it's less. P is less than mu s times n. That means, hey, over here, the last step, f less than equal to mu s times n. Then yes, tipping is going to uh, tipping is going to occur. All right, group problem. We have a vehicle that has a mass of 2,000 kilogram and mu s equals 0.3. The smallest magnitude, we're looking for the smallest magnitude f required to move the car if the back brakes are locked and the front wheels are free to roll. We're going to draw our free body diagram. In that free body diagram, we write our equation. Sum of all the forces horizontally, sum of all the forces vertically, and we're going to do a moment about point A. After that three equations, we also are going to assume that the rear wheels are on the verge of slip. Then we can write our equation FB equals mu S times MB, which come out to be 0.3 MB. And then we have our four equations. We're solving for our four unknowns. Come out to be F. We'll get the value of F, NA, NB, and FB. This is all I want to show you in Unit 8. Thank you for watching.